Hello Mathies, Gatos here. In this video we're going to talk about log functions and how to find the limits of log functions. But before we can talk about log functions, we need to talk about inverse functions. So inverse functions are any kind of a function in which the domain and the range are interchanged. What that means is that x and y interchanged. X becomes y becomes x. You can see that algebraically in this equation here. Y becomes x. So the inverse of y equals f of x is x equals f of y. The domain of the function becomes the range of the inverse. The range of the function becomes the domain. Let's look at that graphically. So in this graph here, you can see I have two graphs. I have y equals b to the x, an exponential graph, and I have y equals log base b of x. So you'll notice in both of these graphs, we have the same base. So the base in the blue graph is the same as the base in the red graph. And in fact, the base of a log and an exponential function are identical, and they behave in the same way. So if I have an exponential function and I take the inverse of that, the bases are identical. And I can see that in this graph because they're both increasing. So that exponential graph must have a base that's greater than 1. And you can see that in the red graph as well. It is also increasing. Let's look at all the particulars. So we learned in our exponential function that if we have an exponential function, it does not have an x-intercept. The reason it doesn't have an x-intercept is because it has a horizontal asymptote at 0. Well, let's look at the inverse of that exponential function. Instead of having no x-intercept, it has no y-intercept. Instead of having a horizontal asymptote, it has a vertical asymptote because x and y interchange. Okay, further looking at it, we have a y-intercept of 1 for my exponential, which becomes an x-intercept of 1 for my log graph. I don't have a vertical asymptote for my exponential function. I don't have a horizontal asymptote for my log function. And you can also see further that they are inverses because the domain becomes the range and the range becomes the domain. So these graphs, the exponential and the logarithmic graph, are indeed inverses of one another. Another way that I can tell graphically is looking at the identity line. Now the identity line is that graph y equals 2x. It's a line. I don't think I'm being able to get it here. Let's just see here. Okay, I'll sketch it in. So this line here, y equal to x, is called the identity line. Called the identity line because the y and the x values are the same. And you can see about that line, it's a reflection. The blue line is a reflection of the red line, or the blue graph and the red graph. They are mirror images of each other about that identity line. So we can use this fact of inverses to help us with the graphs. So let's look, just like we did for exponential, at two different cases. One case where the base is greater than 1. So base greater than 1, you can see looking at this graph here from left to right, I have an increasing graph. Reading it from left to right, you can see that my graph is increasing. My y function is getting bigger. So let's look at the limits. So the limit as x approaches positive infinity. So as I have my graph here, I'm going to look at what happens as my x values get bigger and bigger and bigger. And you can see as they get bigger, the function or the y value approaches positive infinity. Now let's look at what happens when I reach or approach 0 from the right. And I'm approaching it from the right, not the left, because there's a vertical asymptote and I can't approach it from the left. So as my x value gets closer and closer and closer to 0, you can see that this graph actually goes towards negative infinity. Okay, let's look at the other case, and that's a case where the base is in between 0 and 1. So since it's in between 0 and 1, you can see that's a decreasing graph, just like it would be for an exponential function. So if I read this graph from left to right, I can see that my y values are getting smaller and smaller. It is in fact decreasing. And then let's look at the limits. So the limit as x approaches positive infinity. So as I have my graph here, I want to look at what happens as I make x bigger and bigger. So as the x values get bigger and bigger, you can see that my function, my y values, go towards negative infinity. Let's look what happens as I approach 0 from the right. Again, I can't approach it from the left because I have a vertical asymptote there. So as I approach 0 from the right, I get closer and closer to 0. You can see that my graph goes up towards positive infinity. We don't have the case of b equal to 1. In fact, the base can't equal to 1 because we saw in the exponential example, it's not an exponential function if the base is 1. So therefore, the base also can't be 1 when I have a logarithm. Okay, let's try this question here using what we know about logs now and transformations. So if I have the graph of log x minus 3, well, that's compared to the base graph of log of x, which of course you can see in my note here is a common base, which is a base of 10. Now, since the base is 10, I'm going to have an increasing graph. So what do I do to my graph to go from log x to log of x minus 3? Well, using what we know about transformations, that's inside the brackets, which makes it horizontal. Remember, horizontal lies. So this is a graph of the log function that has been moved 3 units to the right. So everything on the graph moves 3 units to the right. So on my base graph, I have a vertical asymptote at x equal to 0. Well, because I'm moving it 3 units right, this also moves 3 units to the right. So I'm going to take this and I'm going to move it 3 units to the right. So my vertical asymptote is going to be at 3. Now normally I have an x-intercept at 1, but because I'm moving it 3 units to the right, this also means 3 units to the right, which is at 4. And I know I have an increasing graph, so just doing a really rough sketch, I'm going to have it coming up and increasing like that. So let's look at the actual graph and see how close I was. Oh, let's line it up like that. And you can see, lined up like that, I was pretty close. So it is an increasing graph, has an x-intercept at 4, vertical asymptote at 3, so it looks pretty good. So knowing the graphs of these functions is really going to help you with the limits. And I recommend visualizing the graph or even sketching the graph to help you find these limits. So let's try a couple questions. So this one here, I have the limit as x approaches negative infinity of the log of negative x. So I'm going to use my graph and my knowledge of transformations to help me. So this graph here, log of negative x, that negative on the inside here is a horizontal reflection. So that means I'm going to take my graph of log x, again has a common base of 10, which makes it an increasing graph, and I'm going to horizontally reflect it. So let's draw the base graph here just to start. So base graph has vertical asymptote at 0. Horizontal reflection is not going to change that. Then it has an x-intercept at 1, and it's an increasing graph. So just a little rough sketch, nothing too advanced, okay, or detailed. So there's what my graph of log x equals. Now, because I have a horizontal reflection, I'm going to flip that to the left and just line it up, and it will look like that. So I went from having an x-intercept at 1 to an x-intercept at -1. Okay, now looking at this graph, reading it from left to right, you can see because I had a reflection, it is no longer an increasing graph, it's actually a decreasing graph. Well, let's look at what happens as we approach negative infinity. So here is my little shape that I'm going to look at, and I'm going to approach negative infinity. So that means I'm going to make x smaller and smaller in the negative direction. So I'm going to start over here at like close to 0, and I'm going to make it smaller and smaller and smaller. So see how x is getting smaller and smaller in the negative direction? Well, you can see that's approaching positive infinity. Okay, let's look at the next graph. So I have log base 3. The base is 3, so that means increasing. And I'm doing x plus 2. So again, this is inside the brackets, which makes it horizontal, but we remember that horizontal lies. So that's not 2 units to the right, it's actually 2 units to the left. So my normal graph looks like this. I have a vertical asymptote at 0. I have an x-intercept at 1, and because the base is greater than 1, I have an increasing graph. Now we're going to take all of that and we're going to translate it 2 units to the left. So I'm going to just take this and move it over 1 and 2 units to the left. So my vertical asymptote is now at -2. My x-intercept is now at -1, but it's still an increasing graph. So let's look at what happens as we do the limit as x approaches -2 from the right, okay? So I want to get closer and closer to the right-hand side of it. So here, I'm going to get closer and closer to -2 from the right, and you can see as I get closer and closer and closer, this graph goes to -infinity. So just knowing what my graph looks like makes these limits super easy. Okay, this one here, limit as x approaches positive infinity of log of 1 over x. So again, no base means it's a common base of 10, which tells me it's an increasing graph. So I just want to write this a little bit differently. I'm going to write it as the limit as x approaches positive infinity of log of x to the -1. 1 over x is the same as x to the -1. Now, of course, using my laws of logs, I know I can bring that -1 down. So I have the limit as x approaches positive infinity of negative log of x. Okay, let's start just with my base graph. So my base graph, vertical asymptote at 0, x-intercept, base of 10 means it's an increasing log graph. So that's just a very rough sketch of what it looks like. Now, this negative in front, the negative in front means it's vertical, and because it's negative, it's a vertical reflection. So that's not going to change my vertical asymptote. It's not going to change my x-intercept. It's only going to change my graph. So instead of it being an increasing graph, I'm going to reflect it. It's going to be a decreasing graph like that. Okay, so my x-intercept still stays the same. So what I want to look at now is I want to look at the limit as x approaches positive infinity. So starting here really close to 0, I want to look at what happens as I make x bigger and bigger and bigger. So you can see as x gets bigger and bigger and bigger along this function, it's eventually going to go down towards -infinity. It's getting smaller and smaller. Okay, this last graph here, I have a base of 0.3. And I know from exponential, the bases behave the same exponentially as they do logarithmically, and that means it is going to be a decreasing graph. Okay, so if I look at that, that's all I really need to know. So my vertical asymptote is at 0, my x-intercept is at 1, and since my base is 0.3, it's less than 1 but greater than 0, it will be a decreasing graph. So something like that. Again, just a really rough sketch. So I want to look at what happens to this graph as I approach 0 from the right. I can't approach it from the left, of course, because of that vertical asymptote. So here we're getting closer and closer to where it's 0. So approaching it from the right, I'm getting closer and closer and closer to 0, never truly reaching it, but getting closer. You can see my graph is going towards positive infinity. Okay, so this is just a little introduction to logarithmic limits. In the next video that I have, we're going to be looking at natural logs. So I hope this video helped, and I look forward to seeing you for the next one, natural logs.